the amino acid sequence. That would be the best description of it. What is the amino acid sequence? And you can see, like on the tripeptide, tetrapeptide, oligopeptide, polypeptide, we start out at the nitrogen end and we move down through the sequence, and it ends with the carbon end, C-terminal end. If you read a paper and it said, here's the amino acid sequence of this, this enzyme, this protein, whatever it might be, they're going to work from the nitrogen end. The very first residue or amino acid, sometimes they'll talk about residue. This protein has 1,000 residues. The very first one is serine or phenylalanine or glycine, whatever it is. So it goes through this sequence. And what is the bonding at the primary level? It's covalent bonding. Covalent bonding. You've got nitrogen, carbon, 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 nitrogen. Nitrogen-carbon bonds. These are shared electrons. These are pretty strong bonds. And the important thing about the protein is to maintain that sequence. Don't want to get an amino acid shifted over to another position. And so to do that, just like what you were doing when I came around and said, oh, that's D, you got to make L, you had to actually break a bond. Those little stems, think of those as covalent bonds. You had to break one and break another one and move it. It actually required the breaking and the making of new bonds to change the position of something in there. So at this point in time, all we have is this long linear molecule. That's our primary structure. People have gotten Nobel Prizes for, like, the ribosome. The ribosome in the cell is a huge protein huge protein structure. Huge. I mean, I don't know how many amino acids would take up, but anyway, someone elucidated the structure of the ribosome. And probably about 7 or 8 years ago, I think they got a Nobel Prize in chemistry for elucidating the structure of the ribosome. So that's structure. Primary structure. Okay, secondary structure. There are two main shapes that come into play in secondary structure: the alpha helix and the beta pleated sheet. Alpha helix and the beta pleated sheet. All right, what you're seeing right here is a little bit of helix or alpha helix structure in a protein. So after you get to the primary structure, now the protein starts figuring out what it's going to do. Secondary structure, we got the alpha helix and the beta pleated sheet. Now, let's take a peek at what kind of bonding is involved here. Here's the alpha helix. And I'll blow this up bigger so we can see it. So in this helix, we're spiraling up through the amino acid sequence here. So we're going from one amino acid to another amino acid to another, spiraling up through here. And what are we doing? We've got a carbon-oxygen double bond right here. Maybe I can see it even a little bit better if I make it smaller. Carbon-oxygen double bond right here. We move on up the helix 2 or 3, 4 amino acids, and we come to another carbon. Here's an NH. There's a carbon-oxygen double bond. But here's the NH that is next to that carbonyl. That nitrogen has a hydrogen on it, and it is hydrogen bonding down here to this carbonyl. This carbonyl is hydrogen bonding up to a hydrogen there. This carbonyl is hydrogen bonding up there. So what's being involved here? Hydrogen bonds. I put that in the wrong place. Should have been right there. So what we're doing is we're getting a hydrogen bond from here to like an NH, three to four amino acids away, and it's curling it into a helix as it does that. So this is hydrogen bonding. And this is from the amide backbone of the protein structure. Hydrogen bonding. Okay, what you've got here is these aren't as strong. These aren't as strong as covalent bonds. If that protein gets bumped around a little bit or twisted or something, those bonds can either break or remake those bonds without changing the amino acid sequence. It would not disrupt the basic structure of the protein to break some of these bonds. I usually always talk about Gulliver's Travels at this point in time. I don't know if you remember that book. Gulliver's big, huge guy. He goes wandering into the land of the Lilliputians, and they freak out. What are we going to do with Gulliver? He's going to kill us. He's going to stomp all over us. He lays down, goes to sleep, and what do the Lilliputians do? They take out their rope, which is like thread to Gulliver, and they string thousands of those ropes across him, and he wakes up and he can't get up. Well, that's what we got here. We got many, many weak bonds that are holding that in a helix. You follow me? They're weak, small bonds, but there's many of them. And they form this alpha helix. We call it alpha helix. And then, but similarly, you can get, so this is just kind of looking at it. If you look down that helical structure, you get the R groups flaring out there. They're not involved. They're just flaring out, and you got this hydrogen bonding going up and down through this cylinder, this helical staircase. Beta pleated sheet is where, think of the protein as a spaghetti, and it's weaving, and now it's weaving back around next to itself, and then weaving next to itself. And again, you get same sort of thing, hydrogen bonding. But now instead of being in a helical pattern, it's in kind of a quilted pattern. It's laid out in a flat plane with hydrogen bonding between the different bended strands. So here's an example. Here's your N-terminal end. You come up here, it weaves back down this way, and you have hydrogen bonding going between the two sides of this. Anti-parallel, this is going this way, now it's pointing this way. Here's parallel, it actually bent again, and now the two strands are going in the same direction, but same sort of thing. NH to C double bond O bonding, hydrogen bonding. This is all secondary structure. Notice so far we haven't said anything about the R group. Now, what's the R group doing there? Well, the R group does a lot, but it does it at the tertiary level. Tertiary structure. I'm going to erase the quaternary because we got to, we'll get to it, but we'll put it separately. Tertiary, we've got R group interactions. Here's where the tertiary structure. Now this is actually where the protein gets twisted into its final conformation. And that final conformation is very, very important. If you were to think of a protein like you would think of a key has a certain structure to it. And the structure of the key is essential to its function, right? This key opens that door. Not many other keys will do it. It has to have this structure to it to fit in that lock and turn that lock. So the structure is an integral part of its function. That's the same way it is with proteins. They look globular. They look like they don't have any real structure to them, but they actually do. They have a very specific structure, and once you disrupt that front structure, it won't work anymore. It won't function properly. So how does it get into that last final structure? Has to do with the R groups. This gets it into its final biological function. Now that doesn't mean this isn't important. It can't get into this final structure without the right sequence to begin with. Okay? Has to have the right amino acid sequence, has to have the right amount of alpha helix or beta pleated sheets along the way, and then finally this twists it into its final conformation. All right, now I'm going to go down through here. This is just a generic protein molecule, and I'm going to, what we got pictured here, let's see, Samantha, would you turn this light off so we can see this a little bit better? What we got pictured here are different kinds of R group interactions. And I'm going to go from the weakest interactions to the strongest. Okay? We're going to work through this from weak interactions, and here's two examples of fairly weak interactions, hydrophobic interactions. Hydrophobic interactions, and this is polar, or excuse me, non-polar R groups. All right, here's an alanine. You could actually look at these R groups coming off of there. Here's our amino acid sequence. So we haven't defined it. You're just going from one amino acid to the next. But if you get over here to this amino acid and you see a phenyl group here, what amino acid is that? Phenylalanine. So we've got a phenylalanine right there, and along in the sequence, however many it is, 8, 10, 15 amino acids later, we've got a phenylalanine here. And what does that give rise to? The possibility for those phenyl groups, they're hydrophobic. All of this is water. This is all an aqueous environment here. And these guys are saying, I don't like an aqueous environment. Let's make our own little hydrophobic patch here. Okay? And they are attracted to one another because they're both hydrophobic. Likewise up there, we have an alanine and a valine. And they're both hydrophobic, and they get this nonpolar R groups. Next, we have polar R groups. Polar. So we might have here, what is this, serine, or what's that first one with an alcohol on it? Isn't it one I had you draw? It's got this R group.
Is that R? Arginine?
not tyrosine. Oh well. What is it? What's serine look like? That's it. That's it. Serine. This is serine. Yeah, I just drew it differently. See, there's serine. Right? Yes? Yeah. This is here, and this is here, and that's there. I'm just drawing the R group. That's serine. So this would be a serine, and this could be another serine over here, and you're getting polar R groups. So what would that be? That would be hydrogen bonding. This is hydrogen bonding. So these are polar R groups, polar interactions. And you're getting hydrogen bonding. Because you have things like OH groups. Here's an amine, so this could be a lysine. And here's like a glutamic acid. Glutamic acid with a carboxyl group on it, and you're getting hydrogen bonding there. So polar interactions and hydrogen bonding, and then here's a salt bridge. So you got the positive charged amino acid plus a negatively charged amino acid, and you get a salt bridge. Salt bridge. So that would be a lysine and a glutamate up there, and you're getting like the ammonium salt of that carboxylic acid. That's a stronger interaction. It's forming a salt. It's an ionic attraction. And then finally, the strongest one is right here. And it's the disulfide bridge. This is specifically cysteines. They're the only ones that end with the SH. And so you have a sulfur-sulfur covalent bond. All right? Instead of having a couple pieces of paper loosely stacked together, you put a staple in it. You've stuck it together with a covalent bond. And we're going from weaker to stronger interactions. This is tertiary structure. What is in common with tertiary structure is it's all involving what the R group is on the amino acids. R group interactions. We only get that when we get down to tertiary structure. Yes?
What do you mean with A?
An amino acid. A.A is an amino acid. I'm just abbreviating amino acid.
So the disulfide bridge is what gives a protein the tertiary structure?
It is one of the things. All of these do. All of these are elements involved in tertiary structure.
Oh.
All of them are. I'm just saying the disulfide bridge is the strongest interaction between two R groups. Yeah, these are all tertiary structure here. This whole, from here on down, deals with tertiary structure. Okay. All right, here's what the disulfide bridge looks like. Four of the teams here made cysteine. You'll see why in a minute. Four of you made cysteine. So here's a cysteine, here's a cysteine. The R group is a CH2SH. You get these two SH's together, you form a sulfur-sulfur bond, covalent bond, and you split out two hydrogens. Or you're splitting out two hydrogens here, forming that disulfide bridge. That's what that is. And we'll form some of those in a minute. Yeah, so types of interactions: salt bridges, hydrogen bonds to polar residues, hydrophobic interactions between nonpolar residues. When you're hearing that word, just referring, they're using that as a synonym for an amino acid, a particular amino acid, a residue. And this is kind of just in a generic way showing how that goes together. So at the primary level, we're looking at the amino acid sequence. We go from one amino acid to the next to the next. Secondary, we're looking at things like alpha helical structure in the protein. Tertiary has to do with the R group interactions, where this thing now is being bended and twisted into a certain shape. All right, so all proteins exhibit primary, secondary, and tertiary aspects of structure. Only some of them, complex proteins. What do I mean by that? Proteins that are made up of more than one unit. Hemoglobin is made up of 4 units, 4 protein molecules. And so it has a 4th level of quaternary structure that refers to how those 4 units are tucked into one another. How are they arranged with one another? That's quaternary structure. All right, we'll see a little bit later. Not all proteins are complex proteins. Many proteins, like insulin, is a single molecule, and there does not have a quaternary level to its structure. Okay, so now we want to now see this play out in the insulin molecule, primary, secondary, tertiary structure. And we've gone through what an amino acid is, how to build these models, how they link together. Now pay attention to this, because we're going to start bringing yours up here. And Samantha, I think we can turn this light back on again. Thank you. We're going to start bringing these up and building our insulin molecule from the nitrogen and moving to the carboxyl, carboxyl. We'll move along in a certain sequence. And what is that sequence going to be? Right here. This is human insulin. This is the amino acid sequence for the human insulin protein. And it is made up of 2 chains, chain A and chain B. Made up of these 2 different chains. The chains are attached to one another through disulfide bridges. There's a disulfide bridge here. There's a disulfide bridge here. Cysteine, cysteine, making a bridge. Cysteine, cysteine, making a bridge. And even in chain A, there is a sulfur bridge. Now, I had you make 1, 2, 3, 4, 5, 6, 7 amino acids. Those 7. So we're going to start out with a cysteine. We're going to link a cysteine through to it. Bring up threonine, serine, isoleucine, and another cysteine. And we're going to just show what we mean by. So we're not starting right there. That would be your nitrogen end there. I imagine that we already did 1, 2, 3, 4, 5 5 amino acids, and we're now here. We're at this point. And we're moving on down through here. We're going to build that, and then we're going to link a cysteine to that cysteine, and that's going to be where this chain B would attach. All right, so who's got the first cysteine? You got cysteine? Come on up here, Alejandro. Anybody expect Alejandro to be bashful? Come on over here. Come on over here. Over here, Alejandro. And, okay, you are the N-terminal end. Turn around. There. Hang on to that. Here is the C-terminal end. So here's cysteine. It doesn't matter what we do with that. We're going to be nitrogen here, carboxyl here. You hang on to that. Okay, second cysteine. Vanessa? And notice that we're not going to get the R groups involved here. It's neat that these are color-coded. You can keep track of these. Here's your cysteine. Here's your SH group. Okay, now you're going to approach this carboxyl group with your nitrogen. Nitrogen.
Okay, hold on. Let's take it up a little bit.
Don't do it.
I know.
Okay, so bring your nitrogen in here. Hang on to your carbon. Bring it in here. Okay, now what happens? What happens? This OH group and this hydrogen are going to form a water molecule. Chelsea, catch this. There you go. There's our first water. There's our first peptide. Hang on to this. You're going to stay there for a while. Okay? Vanessa can sit down as soon as we get 3-9. There's only one 3-9. Who has 3-9?
Nobody?
Nobody has 3-9? Yeah, you have 3-9. Won't be long. All right, Vanessa. So there's our N-terminal end. There's our C-terminal end. Hang on to the C. Bring in the N. Hydroxyl group on the carboxyl and a hydrogen here forms another water molecule. Okay, Chelsea. Chelsea's 2 for 2. All right, so we're forming our amino acid sequence. Hang on to that nitrogen. Cysteine, cysteine, 3 and 9. Okay, hang on to that carbon. What do we got next? Serine. Okay, Genesis, you can sit down. Hold on.
Okay.
Nitrogen's coming in here. Hang on to your carbon. Here's our hydroxyl. Take off of hydrogen. Hold that up for me, please. Okay, Chelsea. Oh, one-handed. Getting too good at this. Another peptide. Another peptide bond. Hang on to your carbon. We now have 1, 2, 3, 4. That's a tetrapeptide. Isoleucine. Okay, Gail. Bring in the nitrogen. All right? This is just a normal pattern. We take off the OH. Can you hold that up for me? We take off a hydrogen. Boy, it is warm in here, isn't it? Chelsea? Hold on to that carbon. See, the R groups are all just dangling down in here. We got one more cysteine. Come on around here. Okay, Danielle. You took the hydrogen off already. Make that water molecule. Throw it at whoever you want to. All right. Hang on to that carbon. Okay, now we've got 5. All right, you two can sit down. All right, here's 5. Now it gets so heavy that some of these bonds start breaking because the model gets so heavy. But we've got a chain, we've got a linear polymer building here, a protein molecule with a line from the nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, right down through here. Carbon, carbon, nitrogen, carbon, carbon, and our end carboxyl group. Now imagine that this carbonyl hydrogen bonds to, let's see, that will go down 1, 2, 3, that it decides to hydrogen bond to this NH right there. And hopefully you can imagine, as that would happen, that we could start forming a helix. And there would be nothing there but an attraction between that oxygen and this slightly positively charged hydrogen. And you'd get that, and then you'd get that from this carbonyl to another one of them, and every carbonyl would be attracted to a certain hydrogen. You get the alpha helix. And so what we've got is that portion right there. You can see the yellow cysteine, cysteine, 3,9-serine, isoleucine, cysteine. We got that on. All right, now, so that's the primary structure. If we got that hydrogen bonding going in there, that'd be secondary structure. This would be UV light or an X-ray breaking a covalent bond. That's what it takes. Radiation would break a covalent bond and mess up a molecule. Okay, so that would be our secondary from the hydrogen bonding. And our tertiary structure is going to have to do with this. So which one is it? It's our very first cysteine to our second cysteine. Someone else help me. Danielle or whoever. Up here and hang on to that. Here's our first cysteine. Here's our second one. So if these, support that for me. If these were to take off a hydrogen and form a disulfide bridge, there's a disulfide bridge, and we get rid of 2 hydrogens. Okay, and so that's what we have right there, right there. So that they're using a long line there to just show you that this is going to fold back onto itself, and those 2 sulfurs are going to bind to each other. So this was the first one, so the amino acid sequence would go off here. This was the last one. The amino acid sequence would continue off of here, and you'd have this little ring in the middle. Finally, we got one more cysteine. Okay, Francesca. All right, where is that? That is the second cysteine right here. Second one. So why don't you bind that one there? No, it's going to be the sulfurs to the sulfurs. Take that off, and then take that hydrogen off. There. So now this is going off to chain B. Got a disulfide bridge holding chain A and chain B together. And if you got down the line a little bit more, you'd get another disulfide bridge. And that's the start. That's 7 out of, I think there are 52 residues there, 52 amino acids. We have 7 of the 52. Okay. Talked about the alpha helix, talked about all these different aspects of the structure. Okay, let me go another 15 or 20 minutes on just a little bit more about proteins, and then we'll we'll turn our attention to finishing the homework assignments. All right? Any questions? All right. Going into it a little bit more, here's a bunch of different proteins. Insulin, 6,000 molecular weight, 51 residues. I said 52. So 51 residues. Cytochrome C, 104, about twice as big as insulin. 104 amino acids. Myoglobin, 153, about 3 times the size of insulin. Myoglobin is in your muscle cells, and it stores oxygen. It's kind of an emergency supply of oxygen. Where? Right in the muscle. In case you have an emergency, you've got oxygen right there. Myoglobin. Hemoglobin is very similar structure to myoglobin, but it is a complex protein made up of 4 units. You can see myoglobin is a single unit. Hemoglobin is 4 units. And each one of them having about 150 residues. You're up to 574 residues in hemoglobin. This amino acid, 26,926 residues in a specific order. Okay? Imagine yourself, you're in Washington, D.C., you are second in the nation in a spelling bee, national spelling bee contest. There's 2 people left, you and someone else. Your last word has 26,000 letters in it. And they have to be in the right order for it to be spelled properly. When your body needs that protein, that's what it's doing. It's spelling that word perfectly. 26,926 amino acids in the right order. Like they said, if this was simple, anybody could do it. And anybody can do it. You just don't know it. You just don't know it. Your body does this stuff. All right, we'll look at it a little bit more in chapter 20. So yeah, if you spelled that out using a letter for each amino acid, then you'd have that, and it's a particular kind of a molecule. Hair is a protein in alpha helical structure. Here's the individual protein molecule wound around into these fibrils, into packets that go down into this thing, and here's finally one hair, the cross section of one hair. Pretty complex. But the proteins like that. And someone was just mentioning a permanent to me in the when we're putting samples in the oven. Here's a permanent. How do they do permanents? So in the hair proteins have disulfide bridges between them. If you treat the hair with a reducing agent, it will break the disulfide bonds, reduce them, addition of hydrogen. You can curl the hair and then add an oxidizing agent and reform new disulfide bridges. Now the hair's curly permanently until it grows out. But it is locking it in chemically in a new arrangement, and that's how you do perms.
Professor, and it will be the same for people that naturally have curly hair? That will be the difference between...
Well, I guess so, and I don't know. I suppose you could do the reverse of this. You could take someone with curly hair and treat it with a reducing agent, straighten it, and treat it with an oxidizing agent, and it would be straight.
And it could be a reducing agent?
But I'm out on a thin limb right now because I'm not a beautician. But yeah, theoretically, I would think, Alejandra, but don't start your next business based on what I just said. Go talk to someone who's been doing this for a while. Okay, they're globular proteins. Sickle cell anemia is the result of one amino acid out of sequence in hemoglobin. Just one amino acid difference. Oh, I want you to see what this heme group is. Hemoglobin. This starts having you appreciate why these proteins have a particular structure. So here is a single hemoglobin unit. So remember, it's got 4 units, or it's a myoglobin. So here is your big protein molecule. This is your heme unit. So what does that look like? So we're going to look at that. It's what carries the oxygen. So myoglobin, 1 heme unit. Hemoglobin, 1 heme unit in each unit. So it can carry 4 molecules of oxygen. Myoglobin can carry 1 molecule of oxygen. So what does the heme look like? You know that if you're low in iron, you get tired. They say your blood is low in iron. You need more iron to make more hemoglobin, functional hemoglobin. Here's where the iron comes in. It's right at the center of this heme. Iron can coordinate 6 things to it simultaneously. 4 of them are these nitrogens that are in this heme unit. 1 of them is down here to an amino acid, and 1 of them are going to be up here to an oxygen molecule. Can hold the oxygen molecule at the top. It's a +2 iron. All right, here's what it looks like. So here's your heme unit. There's your iron. Here's a histidine. Where is it? It's on the protein. The protein molecule is coming around here. There's a phenylalanine right there. There's a valine over there and another histidine above it. And it's balancing this oxygen molecule right in that little pocket, carrying that oxygen as oxygen to the cell where it is needed for the energy. This is heme.
Oh.
You put that into the protein, and then you have hemoglobin. Okay? Hemoglobin would be the name of the entire protein molecule with a heme unit in it. This is just the heme unit. This right here is. This is the heme unit. This is parts of the protein. This is just showing it a little bit more. There's a little bit of a alpha helix over here. Let's see, another picture. Well, that's I guess that does it. All right. Denaturization. When you crack an egg, the proteins are in their right configuration. You start heating it up, you are thermally denaturing it. And you're not breaking covalent bonds, you're just breaking all those hydrogen bonds, and the egg unravels into it just kind of unravels, it loses its protein structure, and it's ruined the protein. And then you scramble it and eat it. You can denature things with temperatures, heavy metals, changing the pH. Okay, so you can kind of look at denaturization and how that works. There's the essential amino acids.